Hello, Math 1090 team. Today I'd like to start looking at section 6.5, multi-stage finance problems. Many finance problems in real life can't be solved using a single application of any of the finance formulas we have learned in the prior sections. Instead, we have to combine multiple calculations, each to represent a different phase or period of the investment. Let's look at some examples. Francine currently has $55,000 in her 401k account at work. And she plans to contribute $5,000 each year for the next 20 years. How much will she have in the account in 20 years if the account averages a 4% annual return? Now, when I read this problem, I want to try and break it up into different parts or different phases. And I notice there are two phases here. There is the portion that describes the balance she already has in the account. And then there's the portion that describes how much she wants to contribute each year for the next 20 years. And each portion of this investment period, or each portion of this investment plan, grows according to a different financial formula we've discussed. Let's look at the first piece, the $55,000 she has in her 401k. Now, the current $55,000 she has in her 401k, that's money that she just has sitting in there and grows over time according to a compound interest formula. So let's describe how this amount will grow over time. With the compound interest formula, remember, we have an initial balance and then we let it grow by some percent over the compounding periods. And we'll let it do it for 20 years. The formula I'd like you to remember with this is that A, the amount that an account has in it, is equal to your initial principal that you start with, times 1 plus your interest rate given as a percent, divided by K, the number of compounding periods per year, raised to the KT. And during this first period of her investment plan, she has that initial balance of $55,000. Oh, 55,000. I put 50,000. One plus, now her interest rate we said was 4% written as a decimal, divided by the number of times that she's doing this, and we're going to say that she's a compounded, what was it, yearly? Every year this happens, so divided by 1. Raised to the 1, you're doing it once per year for 20 years. Okay, let's grab our calculator and see how this looks. 55,000 times 1 plus 0.04 divided by 1, raised to the 1 times 20. Now, obviously, I don't need these ones in here, but I put them in because we have in our formula so we could follow our work. Okay, What I get out of this is at the end of 20 years, this $55,000 by itself, not including that $5,000 she adds each year, but just the initial $55,000, this is going to grow to $120,511. And if I round this to the nearest penny, 77 cents. Now let's look at the second portion of her investment or her investment strategy. For the second portion, we want to look at the planned $5,000 contribution she makes each year for the next 20 years. And this is going to grow according to a savings annuity formula. She's making that consistent deposit of $5,000 every year for 20 years. So it's a savings annuity problem. So for the savings annuity problem, you want to remember your savings annuity formula. So your savings annuity formula, remember, looks like A equals D, which was the amount of your regular contribution, times 1 plus your interest rate written as a decimal divided by K, the number of compounding periods per year you have, raised to the KT minus 1, all divided by R over K. Now let's put in the values that we have here. Your D, your regular contribution, is the $5,000. Your 1 plus your interest rate, again 4%, written as a decimal, done once per year, raised to the 1 times the number of years, which we're doing this for 20 years, minus 1, all divided by R over K, again your decimal, your interest rate as a decimal divided by the number of times you compound per year. Okay. Now remember, when you put this in your calculator, be very careful about the use of brackets and parentheses. Again, my calculator doesn't use brackets, so I'm just use parentheses for everything. And depending on your calculator, or if you just want to feel confident about it, it might be a good idea to use extra grouping symbols on the top just to make sure that you see all of the top is a portion of the numerator. And maybe again, also on your calculator, you may need to put parentheses around this exponent just to make sure all of that appears as an exponent. So here we go. The first parenthesis to start the numerator, the $5,000 regular contribution. Now this bracket will be a first parenthesis. This little parenthesis right here will be a second parenthesis. And it'll be 1 plus 0.04 divided by 1. I'm not going to write the divide by 1 this time. Parenthesis, which will close off this parenthesis here. Now raised to the, again, my calculator clearly makes this all an exponent, so I don't need the parentheses. I can probably also identify that 1 times 20 is just 20, so I'm just going to put 20 here. Arrow over to get out of your exponent, the minus 1. Now for this bracket that we have here, I need to close that off. This will close off the bracket that I had here. And then I'm going to put one more parenthesis to represent this red parenthesis I wrote for my numerator. Nope, wrong parenthesis. Divide by your interest rate. And again, because it's just 0.04 divided by 1, I'm just going to write just 0.04 here. Okay, I hope you're able to duplicate this on your calculator. When I do this, I end up giving the balance of this annuity is approximately $148,890. And if I round to the nearest penny, 39 cents. Now, the original question we were looking at is, how much will she have in her account in 20 years? And remember, her account has grown now for two reasons. It grew because of the $120,000, or it grew because of the $55,000 she started with to $120,000. It also grew because of those $5,000 contributions, which amounted to $148,890. So now we can say the total value of her account is going to be the sum of these values So let's add these up. It'll be the 120,511.77 plus the 148,890.39 for a total balance of $269,402.16. Okay, let's look at another problem. Suppose you invest $150 a month for 7 years into an account earning 10% interest compounded monthly. After 7 years, you leave the money without making additional deposits in the account for another 21 years. How much will you have at the end? Okay, now again, when you look at this, you want to see two different periods to her investment strategy. There's going to be this first period, which looks like a monthly contribution for 7 years. This can be modeled by a savings annuity formula. After that 7 years of monthly contributions, you stop making deposits and you just let the money sit there for another 21 years. Now, since you're not making any more deposits, it's not going to be a savings annuity. This will be more like a compound interest formula. So let's look at each portion of this one at a time. The regular contributions grow using the savings annuity formula. So again, now remember your savings annuity formula. Well, you don't have to remember it. This will be provided on your exams, but for this problem, we need to know the savings annuity formula. So remember your savings annuity formula. The amount that your account will have in it will be D, your monthly contributions, times 1 plus your interest rate divided by the number of times you compound per year raised to the kt minus 1 divided by r over k. Okay, so for the regular contributions, you're making $150 a month contributions. 1 plus your interest rate. Now our interest rate, we were earning 10% compounded monthly. So write that as a decimal, 0.10. We're doing it monthly. We're doing it 12 times per year. Raised to the 12 times t, the number of years. We were doing this for 7 years. So 12 times 7 minus 1. All divided by your interest rate, again as a decimal, divided by 12. Okay, grab your calculator. So it'd be 150. A first parenthesis, represent that bracket. Another parenthesis. 1 plus 0.10 divided by 12. Parenthesis. Now I'd get my exponent. And I keep saying this, but I want you to remember that depending on your calculator, you may have to insert an extra pair of parentheses around this exponent. I don't on my calculator, again, because it's clearly all an exponent. So mine will just be 12 times 7. Arrow over to get out of the exponent. Minus 1. That parenthesis will close off this bracket that we had at the end right here. Divide by the 0.10 divided by 12. Here I get a value of $18,142. And if I round to the nearest penny, 56 cents. Okay. Now, she made these contributions for 7 years, but after 7 years, you leave the money without making any additional deposits. Without making any additional deposits, this is going to grow according to a compound interest formula. So for the compound interest formula, let's remember that one. The compound interest formula says A, the amount in your account, will be equal to your initial balance, your initial principal, times 1 plus your interest rate R divided by K, the number of times you compound per year, raised to the KT. So here our initial balance was the $18,142.56. 1 plus your interest rate, and our interest rate was again 10%, divided by the number of times we compound interest per year, which was 12, raised to the 12, and we were doing this for another 21 years. Okay, so grab your calculator. The 18,142.56. 1 plus your interest rate divided by 12 raised to the 12 times 21. So for that 21-year period, she started with $18,000, but making no contributions, her account balance will grow to approximately $146,871.62. So let's wrap this up just by stating there our answer nicely. So at the end of the total 28 years, the account will have a balance of $146,871.62. Okay, hope this is making sense. Let's try one more problem. This will be the last problem I have in our guided notes. You want to be able to withdraw $30,000 from your account each year for 20 years after you retire. You expect to retire in 30 years. You expect to retire in 30 years. If your account earns 5% interest, how much will you need to deposit each year until you retire to achieve your retirement goals? Okay, so I'm reading this problem. I'm trying to figure out which formulas I can use to describe each part of our investment strategy, each part of our account. And when I read this, I'm looking at two things, actually. There's a portion where they're going to be taking out $30,000 from your account each year. This sounds like a payout annuity problem because you're withdrawing money each year for the next 20 years. But maybe the biggest part of this, as I'm recognizing, it does say that you're withdrawing $30,000. So a payout annuity. You expect to retire in 30 years. So this is before your retirement. And so you're asked, how much will you need to deposit each year until you retire to achieve your retirement goals? And I'm thinking that's the $30,000 that you're going to withdraw. That's your retirement goal. So how much will you need to deposit? Well, here you're depositing money. You're making regular contributions into your account. This looks like a savings annuity formula problem. Okay. So to approach this, to figure out how much you need to save, you actually need to know how much you need in your account first to be able to fund these $30,000 withdrawals. So maybe the first part of this problem is we need to find out how much money needs to be in the account to fund the $30,000 payments during the retirement or payout annuity portion. How much money needs to be there to fund this? So for this, we need to grab our payout annuity formula. So remember, our payout annuity formula is P. This is supposed to be your initial balance, your initial principal. It's going to equal the amount of the withdrawals that you make each time period, or each year for us, times 1 minus 1 plus R over K raised to the negative KT divided by R over K. Okay, so here, our withdrawal that we're going to make each year is going to be the 30,000. One minus 1 plus, your interest rate was 5%, written as a decimal, so 0.05. And we're making this withdrawal once a year, so divide by 1, raised to the 1 times, and this would be the number of years that we're withdrawing money. We're withdrawing money for the next 20 years. Divided by, again, your interest rate, 0.05, divided by 1. Okay, so here we go, the 30,000. For your first bracket, I write it as a parenthesis, 1 minus, another parenthesis, 1 plus, the 0.05. I'm dividing by 1, so I'm not going to write that. Parenthesis, exponent, 1 times 20, that's just 20. Arrow over to get out of the exponent. A parenthesis to close this bracket that was here at the end. Divide by 0.05. Again, 0.05 divided by 1 is just 0.05, so I'm just writing the 0.05. And it looks like this that has an error. And I'm recognizing there's an error because this is a negative number. This can't be right. So I'm looking back to see where I could have messed up, and I'm noticing a common error is I forgot the negative on my exponent. I forgot it my formula too. So if we go back, I think I actually forgot to write this negative. So let's put that negative here. And I don't want to type my entire formula in again, so I'm just going to hit second, enter, and that brings up my formula that I entered last. And I'm going to arrow over and insert a minus there, a negative sign. And for my calculator, the insert is blue right here. It's behind the delete key. So I'm going to go second, insert, and I'm going to put that negative that I forgot. Okay, so this tells me that if I want to make $30,000 withdrawals every year for 20 years, to fund this type of annuity, we need to have starting in our account $373,866 and round to the nearest penny, 31 cents. This is the amount that needed to fund the $30,000 withdrawals each year. Okay, so now we want to figure out, how am I going to get that money? You want to retire. How are you going to accumulate this much money so that you can retire? Well, this is going to be your savings annuity portion of the problem. So we'll say to accumulate this much money in your account, we will save each year during the savings annuity portion. Okay, so for the savings annuity portion, we want to remember that a savings annuity grows according to the model. A, the value of your account, is going to equal to D, the amount of your monthly contributions, 1 plus R over K, raised to the KT, minus 1, all divided by R over K. Now, as it's written, This gives us the amount in the account after making regular contributions D, which is not what we want to know. We want to know how much do you need to put in each year to accumulate to this $373,000. We actually want to figure out what D has to be, our contribution. So remember, we've done this in the past. I want to solve this for D, our contribution amount. So if we solve this for D, remember the way I did that without writing all of my steps each time. To solve for D, I'm going to multiply to get this R over K on the other side of my formula. So if I multiply by R over K, we're now going to have A times the R over K. And then to get D by itself, we're going to divide both sides by this bracketed expression. So if I divide, then now it'll be divide by bracket, 1 plus R over K raised to the KT minus 1. Okay, now our account, we need to have that $373,866.31 times our interest rate, which was 5%, so 0.05. And we're doing this once per year. How many payments each year do they have to make? Divided by the 1 plus, again, your interest rate, divided by 1. We do this once a year, and we're saving, how long we were saving for. Let me go back up here. Said that we expected to retire in 30 years, so we'll be able to save this money each year. So 1 times 30 minus 1. Okay, so grab your calculator. We have 373,866 and 31 cents times the 0.05 divided by 1. I'm just going to write the 0.05. Divide by, now the first bracket to represent our grouping symbol for the denominator. A second parenthesis to represent this one, the small parenthesis. 1 plus, again, your interest rate divided by 1 is just 0.05. Close off that parenthesis for the interest rate. Raised to the exponent of 1 times 30. I'm just going to write 30. Arrow over to get out of my exponent, minus 1. Close off my parenthesis that represents this bracket at the end, which is the grouping symbol for my denominator. And I get $5,627, and if I round to the nearest penny, 22 cents. And to understand this, let's put a sentence next to it. This amount will need to be deposited each year for the next 30 years so that your account will start with enough during retirement to fund the $30,000 withdrawals. So if you make $5,627 a month payments every year for the next 30 years, then in 30 years, you'll have $373,866 in your account. At that point, you'll stop making deposits, and you'll start withdrawing $30,000 each year for the next 20 years. Okay, this finishes all of the problems I have in our guided notes for chapter 6.5. I hope this gives you everything you need to know for your homework, and I hope this video was helpful. I'll see you guys next time.